Today I'll be talking about the work I did along Ripple and Berkeley RDI on building the XRPL zkBridge, or at least making the proposal to later be built. But let me first introduce you what Bridge is. We already saw a great talk this morning in the general session, but Bridge is basically a protocol that allows different blockchains to talk to each other in a safely manner. The important word here is the safely part, because we've seen the previous year that the biggest blockchain attacks have been on bridges, and millions of dollars have been stolen from unsafe bridges that that don't work on trustless assumptions. So a solution by some great scientists from the US, Dan Bonnet here, is the zkBridge, which was proposed in 2022, and it's currently being productized by Polyhedra, which brings three properties that are really interesting. We have the trustless property. We are not trusting any committee now. We have the secure property, which comes from zkP. zkP is mathematically secure. We've heard a lot about zkP, so I won't bother you too much with the specifics, but it's used in this protocol, as we'll see later. And finally, it's efficient, because zkP is not only very secure, but really fast to verify. You could have huge statements that can be verified in milliseconds. Let's first take a look at the zkBridge structure step by step, and then let's see if it can be used on XRPL. So imagine me as a user want to send some tokens from chain 1 to chain 2. We'd first use a smart contract to lock the tokens. It could be done without a smart contract, be freezing techniques on XRPL, for example, and other methods depending on the blockchain. But the important thing is that there's a new block on the blockchain that has a transaction that says that I've locked some tokens. Now, we want to prove to the other chain that there's a transaction in this chain that blocks the token. So how do we do that? There's something called a light client verification protocol, which allows normal users, normal nodes, to verify if a specific block or transaction is in a specific blockchain. So now we'll have a block header relay network. Is basically a group of people that will generate a proof for the correctness of the for the existence of a header in the first chain. In simpler terms, it's gonna, like, the block header relay network is gonna generate a proof that says, hey, in this chain, there's a block that has this header. It's as simple as that. Depending on the chain, that's gonna involve verifying some signatures or verifying a hash function, or it has many methods, but it's pretty related to the consensus protocol. Then this snark that has been generated in the block header relay network is gonna be sent to an updater contract. This updater contract has three main purposes. It stores the headers from the other chain. It verifies the zero-knowledge proofs that are generated by the block header relay network. And it finally updates the headers stored there every time a correct proof is provided. Now we have this new header on this smart contract, which can be minted via another smart contract, and I get the tokens in the other blockchain. Okay, so from an implementation perspective, when you think about how to implement a bridge, you mainly think about this part. We want to implement the part that basically sends the information that, hey, this blockchain has a block that has this specific header. And here we have the way from XRP to EVM Sidechain, but we can also have, and we want to have, the other way around. Let's try to see what happens when we try to do that with XRP. We have XRP Ledger, we have block header relay network that would generate a proof for the light client verification protocol for XRP. We would send that proof to the updater contract in EVM Sidechain, and it would update the header list. Now imagine I'm on the other side. I have some tokens in EVM Sidechain that I want to send to XRP. We would do the same. We would get the block header relay network. It would generate a proof for the correctness of the light client verification protocol. And then here we have a problem. There's no smart contracts in XRPL. So yeah, when that's the problem that we were facing when we tried to first implement the XRP zkBridge. And the question that came to my mind is, Okay, so what does the updater contract really do in a zkBridge? It's the 3 things I mentioned. It stores the headers, it verifies the header, update proofs, and it updates the list when a correct proof is provided. Question now is, can we do that without a contract? The answer is yeah. So let's treat the header updates as if they were transactions. So what happens when we get a new transaction in like super broad sense? We get a new transaction, it goes through a consensus protocol, and it's added to the blockchain. Now, if we get a new header, it's going to go to a consensus protocol, slightly modified consensus protocol, and it's going to end up in the blockchain. If we look deeper into that, we get the new header. It goes through the block header relay network that generates the snark we mentioned. It can be generated because XRP and EVM both have a light client verification protocol. It will generate this snark that will be sent to the consensus protocol. And then the validators of XRPL will verify the proof and then vote to add this header to the header list that's stored later on the blockchain. How this header list is stored in the blockchain is more on the application or implementation side of the bridge. But since this could grow pretty rapidly, one of the proposals was to use a Merkle tree to save space. This bridge now brings the same properties we had with the other bridge. It's trustless. The security of this bridge is based on the consensus protocol of XRP security. It's secure. zkP provides the same security it provides in the classic bridge. And it's efficient because we just have to verify a zk proof, which is very fast, and XRP is known to have a very few amount of validators. Therefore, it will just be verified around 35 times. But the question now is zkP really needed? Can't the validators get the header straight from, it should say EVM Sidechain? The answer is yes. But zkP provides 2 features, like it doesn't provide them, it makes them much better. Because if we had the 35 validators have to verify the light client verification protocol straight away from the other chain, it would just make it really not really efficient, because the light client verification protocol could be very expensive to verify. And also, it improves the interoperability. We just don't need this link between the validators and the other EVM sidechain now. So yes, zkP is really useful in that case. It makes everything really fast. And now let's end up with our work with my work with Ripple when it comes to the implementation. We could just implement one side of the bridge because the other one depends on XRPL being able to verify snarks, which is snarks or starks, which is not yet a possibility. But we got really good results. We used gnark, which is a Go library to generate proofs, and snarkfold, which is a great paper that was released this January that proposes an aggregation scheme for Groth16 instances. Really recommend reading it. Basically the verification, like the proof generation procedure involves generating the proof for the correctness of 35 signatures. Since we are aggregating, we can do that in parallel, and we end up with a 10-second proof generation, 5-millisecond folding time, and 196 bytes of proof size that will be later verified by the validators. Thank you very much. I'm happy to take any questions you'll have.